For bromination reactions, you can easily see that from the reagent given. Bromine molecule with a light would break it down to the bromine radical. That will go for the first propagation step, which is abstracting hydrogen from the molecule. But this has so many hydrogen. Okay? It has so many hydrogen. So which one do you think you would have to replace? That's the question. All right. Well, the more substituted position would be the best position, right? So that one, this hydrogen, that carbon is a tertiary carbon. So tertiary carbon makes a tertiary radical. The tertiary radical is the most stable among tertiary, primary, secondary, those series. So I think this would be a pretty good place to start. Tertiary radical pulled out. I mean, made it happen by taking these hydrogens away. That radical pulled out the bromine, then you're going to produce this bromination done at the tertiary position. Sounds very reasonable, right? Even though you are able to do that, my suggestion is do others as well, because sometimes you get surprised. So what other position, I mean, whatever you don't do that, this position, can you make the bromination happen at that position and produce something like this? I see this a lot. People see the bromination Bo2 like given to the molecule. They kind of memorize, oh, I just have to put the bromine somewhere. I just erase that one of the hydrogen out, put the bromine there, then we get the product. So they heard probably the most crowded position will be the best, like this tertiary position. That's even more, right? That has a 1, 2, 3, 4 carbon there. Best place to put it. But you cannot make the 5 bonds, so I'll just erase one of the methyl to put it there. That you can simply just randomly guess. If you do it, that will be wrong, right? Because you just cut the one methyl groups away from the molecule for nothing. So don't guess. You really have to work it out. You gotta have a mentality of doing the mathematical questions when you're dealing with organic chemistry question. This is something you gotta work it out, not just guessing or patronizing, whatever. All right. Other positions. There are primary hydrogens. I know that's probably not the best positions, but let's still put it. You take the hydrogen from the primary carbon, that radical is going to be there. And then when you pull out this radical, pull out the bromine, you get that bromination there. That could be the possibility. I'm basically laying out all the possibilities on the table right now. How likely or not, this will be what we describe later. There's another hydrogen on that position there, right? There's another hydrogen there. That's a primary. So that will make another primary radical that put the bromine there. Then you got the bromine there. That's also possible. There's another primary position right here. This has just one carbon bound to it. That's a primary. So typically, when you heard so many times, tertiary is good, secondary is next, and the primary is bad. When you're dealing with this question like this, you go for the tertiary position, and then you get out that's most the product. You stop there and move on. If you don't check all other possibilities, then you don't find this one out. This is a primary carbon having only one carbon substituents. Typically bad. But these carbon substituents having there is a benzene. Right? That's what makes a difference. That's a primary radical can be formed by taking these hydrogens away by the bromine radical. You get the radical. That one will have a multiple resonance structures. This is another thing that you probably want to know. That's called the benzylic position. Carbon next to benzene. Benzylic position is even more reactive than an allylic position because it can make so much resonance structure. It's a primary, so you may think that primary is not going to be the subject of the reaction, it's not going to go well. That is a primary and benzylic, which means a make a resonance structures. So this one is this radical is more stable than even the tertiary radical we just talked about. Even though it's a primary, it's a make a resonance structure. So if this radical go for the reaction, then you get the bromine attached on this position, you get to form this. One of the things I'd like to clarify here is allylic radical, you got the resonance structures, both form can go for the reactions. In the case of the benzylic radical, none of these three will go for the reaction, even though they can make the resonance structures, stabilize the radicals, but neither of these three will go for the reactions, all because if these radicals, any of these three go for the reaction, you get the benzene broken, which is a huge penalty for the molecule. They want benzene intact in the end. Benzene can help it out, but they don't want to break the benzene. So because of that, they want to keep the benzene. These are minor contributors. So these are not going for the reaction. It doesn't mean that minor contributors of the allylic radical doesn't go for the reaction. Allylic, they really truly they can happen both ways. But in the case of the benzylic, these only helping out. They're not going to participate in the reaction, all because they want to keep the benzene. Having a benzene intact is one of the most imperative for the molecule because that's stabilized. So that's the reason why only this one go for the reaction, having a bromine introduced at the benzylic conditions. So, showing that, sorry, going forward. So we already talked about these things are not going to be done because that was purely gas product. But that's the tertiary, and that's a primary, these are primary. I mean, primary, without having no resonance structure, these two are probably really bad choices. That's not going to happen. You got possibility of the tertiary or being primary, but this primary being a resonance stabilized. So I think these would probably major. That's going to be the minor product because the resonance structures really stabilizing intermediate, even as a primary. One of the things that, I mean, that's the reason I crossed it out, not as a major product. I'm not saying that this will never form, but as a major product. One of the things I don't want to do, taking out the hydrogen from the benzene or double bond, telling you, those hydrogen on sp2 hydrogen carbon, radical will never be able to take it out. So you can take out this hydrogen there, make a benzene radical, that put the bromine on the benzene ring. These reactions are not happening, all because you cannot take these hydrogens out. So that one's out. So that's the major problem. So this is what I explained. And then I asked this question in the text. It's all pretty similar. That's the word it is. The question test questions in the text. It looks very similar to maybe what you have seen, but they're not identical. That can complicate the situations. So let me tell you what you need to consider about it. This is what we did. It looks almost the same. That and this. So bromination reaction, same thing. We got talking about bromination at the tertiary position, right? That's this one. We got bromination there. That's this one. And then we got bromination here. That's that one. Among these three, which one will be the major? The previous one, half this was a major because that's the benzylic position, benzene stabilized resonance structure there. That becomes a major. But when you do this one, you're going to find out this is not the major anymore. I'll explain why. These are three hydrogen. I'm not going to consider these primary without being resonance stabilized. Now you know this is not going to be something that will be the major products. So these are the benzylic and benzylic position next to benzene. These are tertiary position we did it here. But that position, it used to have two methyl group, no hydrogen. Now I only put one, so that means it has a hydrogen there. These hydrogen can be taken out by the halogen now. So what we did previously, we take this hydrogen on this position, benzylic position, make this radical. This is a resonance stabilized radical, you know that. That one, we take this hydrogen for the tertiary position. That's a tertiary is good, but this is not resonance stabilized, unfortunately. Too far from the benzene. Now this one, that's the one tertiary hydrogen. You take it out from the bromine radical, then you got the radical form right next to benzene. That's a tertiary and benzylic. The previous question doesn't have that because we got two methyl with no hydrogen. So we don't need to consider that. I just take the one methyl out, having a possibility forms. When the radical forms, this will be the best. That would be better than this one, right? Because of both of them, benzene gonna stabilize it, make a resonance structure. I'm not gonna, I drew it, yeah. I drew the previous slide, so I'm not gonna go for that. This is a benzenic and primary. That's the benzene, this is gonna be stabilizing this radical by making the same type of resonance structures, but that's a tertiary. So benzenic and tertiary is better than the benzenic and primary. So because of that, this will be the major product in this question. You see how the answer changes depending on what the structure looks like? It becomes very subtle. That's the level of the detail that you need to get result for the test 2. So this is, we're not even studying the chapter 2 questions yet. This is just the chapter 4 question, put in the right context, showing you the complexity you have to deal with to get to the right answer. Anyway, so I hope that you understand what type of things you need to look for.